Hello class, this is going to be our first online video for Math 84, and this is a lecture on section 5.3, which is called the Gram-Schmidt Process. The Gram-Schmidt process is a process for getting a basis of vectors that is orthogonal that spans a given set. So let me review something from before. Okay. Recall that P of W onto V, this is called the projection of W onto V, and this is defined to be the inner product of W with V divided by the norm of V squared times V. Remember, this is called the projection. It's actually called the orthogonal projection. And just to give you an idea of what it looks like, if this guy is W and this guy is V, then the projection of W onto V is, if you form a right angle right here, and this guy right here is the projection of W onto V. Okay? Now, the idea here is that part of W is already contained in V. And so what you would do is you would subtract that away from W. And if you do that, you get this vector right here. This vector right here, this guy, is W minus the projection of W onto V. Okay, so here's the idea. The idea is that we are trying to take vectors and we are trying to figure out a way to span the same set as those vectors do. However, we also want them to be orthogonal to each other. So let's first check, because according to my picture, it seems like P and this, V and this guy are orthogonal. So let's actually check that this is true. So check for orthogonality. So what we're going to do is we are going to take vector V and we're going to check what the inner product of V with W minus P of WV is equal to. In other words, we are taking these vectors and we're checking to make sure they are actually orthogonal by using axioms. So if we do this, we end up with, well, using linearity and the distributive property, doesn't this equal inner product of V with W minus the inner product of V with P of W V? What does this equal? So this guy is still here. But this guy right here, so this, I'm going to replace P with that. So what do I end up with? I get minus V with this. Yes, I do have an inner product inside of an inner product. I know that seems confusing maybe, but an important thing to realize is that this thing right here that I'm putting a box around is just a scalar, and so I can pull it out of the entire inner product, right? So what do we end up with? Here's what this becomes. This whole thing becomes V, inner product V. Sorry, that should be a W. V, inner product W, minus, I'm going to take this scalar that I just wrote down and pull it out in front, because that's something you can do with inner products if you remember our axioms. So this becomes W, inner product V, divided by the norm of V squared, times what's left after you pull that out is just V inner product V. But isn't V inner product V, doesn't this entire thing actually just give you the norm of V squared? I mean, that is actually the definition of a norm. So what that means is that this guy cancels this guy, but then you just have VW minus WV, which is the same as the scalar 0. So what does this mean? This means that this process actually works, right? Because when you take this inner product, we got 0, which proves that they're orthogonal. So this picture over here, this picture right here, is accurate. So this means that W and, oops, let me fix that, V and W minus the projection of W onto V is, or are orthogonal. Okay. What about their span? Well, we can clearly see in the picture that they span the same thing, right? In other words, if you look at V and that guy, so also the span of V and W is the same as the span of V with W minus that projection. Because all we're doing is subtracting away something that's contained in V anyway, right? The projection is a multiple of V, so we're not losing anything by taking that guy away. In other words, what have we done? This leads us to a method that yields an orthogonal set of vectors that have the same span as another set of vectors. Okay, so this leads us to a theorem. This is going to be called the Gram-Schmidt process, and it's algorithmic. In other words, it's an algorithm that you have to go in order. So let's do this on the next slide here so we have space to write. So theorem. This is called the Gram-Schmidt process. So let's suppose that you start with m linearly independent vectors, be a linearly independent set of vectors in an inner product space V. Remember what an inner product space is? It just means that we are a vector space that has an inner product operation. Then an orthogonal basis for the span of those vectors is going to be, we'll call these the V's instead of the X's. Where? Now this is how we're going to construct these V's. V1 is just x1. So the first vector is just going to be take x1. Okay? No big deal. Now what about the second vector? We get the second vector by taking the second vector on the list and subtracting away the projection of that second vector onto the first vector in our new space. Okay? What about V3? The way you get the third vector is by taking the third vector in our original list and then subtracting away its projection onto the other two vectors we've already created. So minus P of x3 onto V1, and then also subtracting away P of x3 onto V2. So each time we take a vector and we subtract away its projections onto the other two, and so what we're doing is we're getting a brand new vector that is orthogonal to each one. You continue this process, and the last one will be Vn. Sorry, there were m of them. Vm, which is going to be to take the mth guy and you subtract away P of xm onto V1 minus P of xm onto V2 minus, you do this until you reach the last one, xm onto Vm minus 1. Okay, so you do have to do this m minus 1 times at the very end. Now the way we can write this whole thing as a sort of a shorthand here, so this entire thing can be written instead as the sum from I equals 1 to, let me back this up a little bit. Let me make it a little closer here. So this whole thing is going to be I equals 1 to m minus 1 of the projection of xm onto vi. Okay? So that is the process. This builds an orthogonal basis. This is the Gram-Schmidt process. So V1 to Vm is an orthogonal basis for the span of the original m vectors. Now it's important though that the original m vectors should be a linearly independent set of vectors. Okay? Why do they have to be linearly independent? Because if you subtract away, for example, if two vectors are contained in the span, then actually it is possible that when you use this process, you're going to create the zero vector. Because there's not going to be anything left when you subtract the projections away. So this is why it's important that you do need to start with a linearly independent set of vectors. If you start with a linearly independent set and you use this process, then you're going to end up with a linearly independent set that spans the same thing. Okay? Let's do an example. Obtain an orthogonal basis for the subspace of R4 spanned by the following three vectors. We've got x1, which is equal to 2, 1, 0, 0, x2, which is equal to 0, 0, 9, 0, and x3, which is negative 4, 0, 0, 9. Now, to do this, let's not forget our formula that we are going to be using for all of these parts, okay? Our formula that we need to remember, well, we actually have two formulas, I guess, the Gram-Schmidt and the projection, but I wanted to write down the projection formula because we are going to be using this a lot. Projection of W onto V is equal to W V divided by the norm of V squared times vector V. Okay? All right, so this is important. I'm going to box this. We're going to need this to do this entire part. So let's start by creating a V1. What is V1 equal to? V1 is just x1, which is going to equal vector 2, 1, 0, 0. So nothing to it, nothing to that one, right? But let me go ahead and box this guy. This is one of our vectors that we're looking for. Now for the second vector, we are going to need to do the projection of x2 onto all the v's we've already created. In this case, we only have one v that we've created so far, which was the original vector. So what would the projection of x2 onto v1 be? Okay, look at the formula over there, okay? When you project, you have to do x2 inner product with v1 divided by v1 squared all times v1. And what is this equal to? So x2 inner producted with v1, let's look at the two vectors here. We get 0 plus 0 plus 0 plus 0. So this is actually going to be 0 plus 0 plus 0. Let me erase this here. Plus 0. I don't even need to go further here. Since I'm taking 0 and I'm dividing it by the norm of v1 squared times vector v1, what is that equal to? That's actually equal to the 0 vector. And so when I'm doing v2 is going to be x2 minus this projection I just figured out, which is equal to, it's going to be 0, 0, 9, 0, minus the 0 vector, which is just 0, 0, 9, 0. Okay, so we've got our second vector here. Okay, now what about our third vector? Our third vector is going to equal the third vector on our original list minus the projection of x3 onto v1 minus the projection of x3 onto v2. Okay, so let's go ahead and do these projections. The projection of x3 onto v1 is equal to the inner product of x3 with v1 divided by norm of v1 squared times vector v1, which is equal to, let's see, what's the inner product of x3 with v1? We get just the number -8, right? So we get -8 over the norm of v1 squared is just 2 squared plus 1 squared, which is 5, times vector v1 is 2, 1, 0, 0, which is -16 fifths, -8 fifths, 0, 0. Okay, we're going to need this, right? This guy right here is what we're going to replace this with. Now, what about our next one? We need to do the projection of x3 onto v2. Let me do that on the next slide here. Projection of, let's do that. Projection of x3 onto v2. So projection of x3 onto v2 is going to equal x3 inner product with v2 divided by the norm of v2 squared times v2. But if we actually go back and look at what the inner product of x3 with v2 is, you look at x3 and you look at v2, you actually get the scalar 0. So if we come back here, that means that this is just going to equal 0 over stuff. It doesn't really matter. We don't need to calculate anything else because 0 times any vector is the 0 vector. So that 0 vector, if we come back to the last slide, that 0 vector is this guy. So this guy right here is the 0 vector, right? So this entire thing then is just going to be x3 minus that projection. So what this means is that v3 is going to equal x3, which is -4, 0, 0, 9, minus that vector, -16 fifths, -8 fifths, 0, 0. What do we get when we subtract these two vectors together? Well, -4 minus -16 fifths, that's the same as plus 16 fifths. So that's -20 fifths plus 16 fifths is -4 fifths, right? -4 fifths. And the next one is 0 minus a negative 8/5 is 8/5. And then 0, and then 9. So there you go. There's our third vector. So here they are, right? We've got V1 is right here, V2 is right here, V3 is right here. The point is that we have just created an orthogonal basis for the span of the original. Let's go ahead and write our answer. Okay. This implies that the orthogonal basis for the span of x1, x2, and x3 is, what were our vectors? Our first vector was 2, 1, 0, 0, 2, 1, 0, 0. Our second vector was 0, 0, 9, 0. And our third vector was negative 4/5, 8/5, 0, 9. Notice that these are not necessarily orthonormal, right? These don't necessarily have size 1, but you could turn these into unit vectors if you wanted to. So this is an orthogonal basis. You could easily turn it into an orthonormal basis. Okay, so we're going to do one more example here. Let me write down the problem. Let's again determine an orthogonal basis. And this time we're going to be dealing with functions, so this should be a fun problem. So determine an orthogonal basis for the subspace of the following we're going to look at the vector space C0 from -1 to 1. Remember, this is all continuous functions on the interval -1 to 1, spanned let me back up here. Let me just remind you guys that this is using the usual inner product spanned by the following three functions. So let me actually start writing this on the next page so we'll have more space here. So the three functions we're going to be looking at are f1 of x equals x, f2 of x equals x cubed, and f3 of x equals x to the 5th. Okay. So I'm going to call the new set G1, G2, and G3 for our orthogonal basis. So starting with G1 of x, remember G1 is just going to be F1. When we use Gram-Schmidt, we don't change the first vector. So the first guy is x. Next, what would G2 of x be? Remember, this is going to be our second function, f2 of x, minus the projection of our second function. So it's going to be the projection of f2 onto G1. So what is this equal to? Let's do this side work over here. So the projection of F2 onto G1 is going to be F2 inner product G1 divided by the norm of G1 squared times G1. All right, well, what is F2 inner product with G1? Let's do these inner products on the side here. Well, maybe I'll actually do them right here. So F2 inner product G1 is going to be the integral from -1 to 1 of x cubed times x. Oh no, sorry, F2 is x cubed. Oh yeah, it is x cubed times x. X cubed times x dx. So this is the integral from -1 to 1 of x to the 4th dx, which, since that's an even function, I can do double the integral from 0 to 1 of x to the 4th dx. This is equal to 2 times 1/5 x to the 5th going from 0 to 1. So if you plug in 1, you just get 1, so this is 2/5. Next, what is the norm of G1 squared? The norm of G1 squared is equal to the inner product. Well, let me back up here. It's the inner product of G1 with itself, right? So the inner product of G1 with itself is integrating from -1 to 1. Just take G1 and multiply it by itself. It's x squared dx. So if you actually multiply that, integrate that, this is actually twice the integral from 0 to 1 of x squared, since it's an even function, which is going to be 2/3 x cubed going from 0 to 1, and this is just 2/3. And so we are ready for using both of these pieces. This means that, so if we take this guy and plug in what we know, this is going to equal what? So this is equal to F2, which is x cubed, minus the projection that we just figured out. Remember, the projection's going to be, look over here, right? We need to do this right here. We got to do F2G1 divided by norm of G1 squared times the polynomial G1. So this is going to be F2 with G1 is 2/5 divided by 2/3 times G1. What is G1? It's just x. So what happens? The 2's cancel, you end up with 3/5. So the polynomial is x cubed minus 3/5 x. And I'm going to go ahead and circle this. Okay, so this is my second guy in my orthogonal basis, and I need one more. So for my next one, G3 of x is going to be, so I take F3 of x, and I have to subtract away the projection of F3 onto G1 times, or minus, sorry, the projection of F3 onto G2. Okay, so let's do that. Let me do this on the next page. So the projection of F3 onto G1, the projection of F3 onto G1 is going to equal, we've got to do some inner products in a moment, but I need to do F3 inner product with G1 divided by the norm of G1 squared times G1, right? So we already know what the norm of G1 squared is. I just have to do F3 inner product with G1. So what is F3 inner product with G1? This is going to be the integral from -1 to 1 of, what was F3? F3 was x to the 5th times x. X to the 5th times x, and then dx. What is this going to equal? So this is going to equal, so this is actually equal to -1 to 1 of x to the 6th, and so it is an even function still. So this is double going from 0 to 1 of x to the 6th, which is 2/7 x to the 7th going from 0 to 1, which is 2/7. So this guy right here is going to go up here. And we already know what the norm of G1 squared is. In fact, in the last part, we saw that was 2/3. And so this is going to be 2/7 divided by 2/3 times, what was G1 again? It was x. This is 3/7 x. Okay, so what we just found, this guy right here, if we go back, we just found this guy. So this guy, let me go ahead and fill it in here. This is 3/7 x, so 3/7 x. And now we need to find this guy. Let me go back on the other page. We want to do the projection of F3 onto G2. The projection of F3 onto G2. So to do this, we need to do the inner product of F3 with G2 divided by the norm of G2 squared times G2. What is F3 inner product G2? This is going to be a little bit more complicated of an integral. We are going to be integrating from -1 to 1 the function F3 times G2. So if we come up here, the function F3 is x to the 5th. So let me write that down. And then G2, if we come back here, G2 is x cubed minus 3/5 x. So this is the integral that we have to do. So this integral is what? Let's see what we get here. When we actually multiply this out, we get x to the 8th minus 3/5 x to the 6th dx. Again, those are even functions, so we're going to double and go from 0 to 1. X to the 8th minus 3/5 x to the 6th dx, which is equal to, let me back up just in case I need more room here. This is equal to 2 times, we got 1/9 x to the 9th, minus 3/35, because I'm multiplying by 7, x to the 7th. And we're going from 0 to 1. So if we actually multiply that out, we get what? Let's see here. This is 2 times 1/9 minus 3/35. Again, F3 inner product with G2, right? If you multiply that out, you do get 16/315. 16/315. So right up here, this is 16/315. Now, what about the inner product of G2 with itself? This one I've already worked out in advance, so let me go ahead and write that on the next line. We're going to do the norm of G2 squared. So the norm of G2 squared is actually equal to the integral from -1 to 1 of the function g2 squared. What is the function g2? It's x cubed minus 3/5 x squared dx. So I already worked this integral out. If you work it out, you get 8/175. So if we come back here, this part is 8/175. So the projection, we can cancel 16 with the 8, that is 2/1. So if you were to multiply this out, you would get 350/315 times G2, right? 350/315 times G2. So let's write this down. Times G2. What is G2? Let's go back. G2 was actually the polynomial x cubed minus 3/5 x, right? X cubed, right? This is G2. So x cubed minus 3/5 x. This is x cubed minus 3/5 x. So this is our projection, right? This is the projection of F3 onto G2, okay? And let me go ahead and circle that guy. So what is this? All of this is so that we could figure out what G3 is, right? If you look at G3, coming back, that's right here. So let me put in what we just figured out. 350/315. Let me match what I did over here. 350/315 times x cubed minus 3/5 x. So this is what I have here. What is F3? Well, F3 is just x to the 5th. Okay, so we put it all together and we get the following for G3. We have x to the 5th. This actually does reduce to 10/9, so let me go ahead and write that in. So this is a 10 and this is a 9. And if you combine these three polynomials, you put it all together, you actually do get x to the 5th minus 10/9 x cubed plus 5/21 x. Okay, and this is our G3. A lot of work to find that last one, but we have just finished building our orthogonal basis. So let's go ahead and write the answer down at the end. So what we get is an orthogonal basis for the span of F1, F2, F3 is the polynomials, or the set of polynomials x, and then we had x cubed minus 3/5 x. And then our third polynomial was x to the 5th minus 10/9 x plus, this is x cubed, plus 5/21 x. So this is our orthogonal basis. Okay, that concludes our video. Thank you for watching.